Good morning, everybody, and thank you to the organizers for giving me the opportunity to give this talk. So today what I'll talk about is using simulated quantum annealing to compare some of these all-to-all connectivity schemes that are now being proposed. So I'd like to first thank Wolfgang for actually doing a great job of laying the groundwork. So my job will now be easier. And this work was done in collaboration with Walter Vinci and Daniel Ladar at USC. And all the details, which I'll be sort of skimming over, you can find on this archive reference. So as we all know, right, many interesting optimization problems can be mapped to Ising systems. But of course, the price we have to pay is usually that these Ising systems involve all-to-all interactions or long-range interactions. Right? So here I just show the case of having 12 logical spins, and they're all connected to each other. And of course, the problem with this is that if I'm going to build a device that tries to implement this graph in hardware, it's going to be impossible because I can only really do local connections. And of course, the solution that we've all known for a long time is that the trick is just to map the logical problem to the physical connectivity graph that I have available to me. So Vikki Troy, many years ago, taught us how to do this, at least for Chimera, right? And at least that's the case I will focus on, right? And what she taught us was that if I have n logical spins that are fully connected, I can minor embed that on an L by L Chimera graph, where L is equal to 4n, where what I do is I take the logical spin and I just extend it into a chain. Okay? And this chain has a length of the ceiling of n over 4 plus 1. And I give you here at least a sketch of what this looks like for this n equals 12 problem. And so for example, you can see that this, or maybe it's hard to see, the spin 7 is now, there's 4 copies of it. And what's important is that I actually have to couple these spins ferromagnetically to essentially ensure that they point along the same direction, right? Or if you like, I'm essentially trying to penalize energetically this chain from breaking. Okay? So I might use this language in this talk where I talk about the logical spin being broken, which just means that my chain is no longer either fully up or fully down. So this is the scheme that we've all been working on for, or at least using for a long time. But now we have the Lechner Hauke Zoller scheme, which was first introduced last year. And Wolfgang just described it to us. So let me very briefly describe it again. So the idea is that you take your logical couplings, Jij's, and you map them to local fields. Okay? So now, since you had n times n minus 1 over 2 couplers, you now have n times n minus 1 over 2 physical spins. And essentially, the value of your logical coupling becomes the value of the local field on that physical spin. Now, in order to make this mapping work, what you need to do is introduce FourBody interactions, at least in the original scheme. That's the simplest way to do it. And essentially what this FourBody term will do is that it will essentially energetically favor physical states that can be mapped to logical states. Right? And what Leichner and Al showed us is that you can essentially use this to build this now very familiar triangular lattice, which essentially implements your original logical problem. And of course, what's nice about this is that it fits very nicely on a two-dimensional layout. Now, when an error occurs, right, so here an error is some spin flip, essentially you will violate one of these FourBody terms, and essentially you can measure that, and so then you would know that an error occurred somewhere. So what's our dilemma? Our dilemma is that, let's say you want to build your quantum annealer, and you want to pick which architecture to use. Do you want to pick the minor embedding way, or do you want to do the LHZ way? So what's good about both methods is that we know that if you make the penalties or the constraints very, very strong, then they decouple, if you like, the consistent physical states from the error states or the spurious states. Right? So in this way, you can at least have a good control and remove at least, or push away energetically the bad states in the Ising spectrum, so only in the classical spectrum. The bad is that, of course, the standard driver, right, doesn't care or distinguish between the consistent and the spurious states. So your quantum spectrum actually is a mess, right? It mixes these two states, and this makes life very difficult, right? And in particular, sort of the main focus or the main point I want to push in this talk is that when an error occurs in the middle of your evolution, this error evolves to something highly non-trivial by the end of the evolution, okay? And this is why, or is a big reason why fault tolerance for adiabatic quantum computing or quantum annealing is very, very difficult. This is why we haven't been successful so far. And I really like always to cite this paper by Kevin, Mohan, and Robin, because I think they did a great job of sort of just laying all the various issues that we have with fault tolerance for AQC. OK, so what I'd like to do is at least I would like to sort of come up with a model for the errors in quantum annealing that will be relevant to us, right? So we all know, for example, we can have diabatic errors. And this is just simply because we're evolving too quickly. And of course, it's easy to overcome because you just need to evolve more slowly or have a larger annealing time TF. But of course, you can also have errors because you're interacting with some thermal bath. And here, of course, the longer your anneal is, the more time you're interacting with the bath, so there's a problem. For today's talk, I'm going to restrict myself to at least what I think to be the most benign error model for quantum annealing. And that's, if you like, weak coupling to a thermal bath. And what does weak coupling to a thermal bath mean? It means that essentially the decoherence is happening in the instantaneous energy eigenbasis. So let me describe what that means for us today. So here, for simplicity, I'm just going to consider two energy levels. So let's say this is my ground state, and this is the first excited state. And essentially, decoherence in the energy eigenbasis will just mean that I'm going to have thermal excitation and relaxation between these energy eigenstates. So I have here the energy, the gap, or the instantaneous gap is going to be delta T. And the key thing to remember is that thermal excitations are suppressed by e to the minus beta, where beta is the inverse temperature times the instantaneous gap. So what does this mean? It means that early in the evolution, when the gap is large, thermal excitations are suppressed. As the gap gets smaller, you start getting more thermal excitations. When the gap gets to its minimum, you get lots and lots of thermal excitations. And then when the gap opens up again, maybe if you're lucky, you'll get some thermal relaxation. But rarely does the thermal relaxation sort of bring you completely back to the ground state. Unless, of course, I mean, you wait a really long time here. And again, I emphasize, when this thermal excitation happens here in the middle, it can evolve, or that error can evolve to something highly non-trivial at the end. So I want to use this error model to compare now the minor embedding scheme to the LHZ scheme. So let's just do sort of some number counting. So if I want to consider a spin system of 8 spins, so a logical 8 spins, in the minor embedding scheme, this corresponds to having 24 physical spins. And in the LHZ scheme, it corresponds to having 28 spins. And if I want to consider 16 logical spins, I'm already up to 80 physical spins for the minor embedding and 120 for LHZ. So trying to do a microscopic simulation is definitely impossible. Even doing a master equation approach is not feasible. But what we've learned, at least a lot at this conference, is that quantum Monte Carlo is a good sort of substitution, right? And the way I like to think, at least, of quantum Monte Carlo when it comes to trying to use it as a model of a physical quantum annealer is that you can think of the quantum Monte Carlo updates as sort of pushing you towards the instantaneous Gibbs state. And that's kind of like you're decohering in the instantaneous energy eigenbasis, right? So our method of choice for today is going to be simulated quantum annealing, which we've heard a lot about in this conference. So let's think about simulated quantum annealing and the kinds of errors you can have. You can imagine essentially doing your simulated quantum annealing simulation with not enough number of sweeps. And in that case, essentially, you're not allowing your system to follow, if you like, the instantaneous Gibbs state. So that's kind of like the diabatic errors. And it's also essentially, you're not giving your system time to thermalize. And then, of course, you have thermal fluctuations, and these I'm going to think about as thermal errors. Now, what's important is that in your simulated quantum annealing, again, when these errors happen, sort of in the middle, they don't appear as random single spin errors by the end of your evolution. And if you're still not convinced about using SQA as a model for quantum annealing, at least it's been successfully used, at least in capturing many of the features of the D-Wave processors. So that's just yet another reason that maybe it will be OK for doing this comparison. OK, so let's think about what errors look like for minor embedding. So here I have an ideal chain. So here my red will mean that the spins are in their correct orientation. If my error model was just random errors, I would just sprinkle some errors, and there would be, in principle, no pattern to them. But of course, when we do quantum annealing with chains, usually what we find is that the errors appear as domain walls. OK? So definitely, this does not look like that. Now, in practice, what do we do when we're doing minor embedding? When we have broken chains like this, what we just do is we just take a majority vote on the chain to determine whether the logical spin is pointing up or down. So now let's do the same thing for the LHZ scheme. So let's first consider what errors look like when I have random errors. So here I've sprinkled 4 spin flips. And what you should notice is that when there's an error, it's accompanied by essentially violating 4 constraints surrounding that error. OK? Now, of course, if the errors are very, very sparse, you can sort of see these errors by eye and correct them, right? But actually, people have been working on this, and they've actually developed very, very good error correction schemes when you have random errors. But when we run our SQA simulations, these are not the kind of errors we see. Okay? Instead, what we see are very, very few violated constraints. Okay? So essentially, we see no violated constraints except, let's say, one here and one here. And then you're led to wonder, OK, which spins do I have to flip to actually get those kind of constraint violations? So here I just showed one set of these. So for example, I can get this, this constraint to be violated by essentially flipping all of these spins. And I can get this constraint to be violated by flipping all of those spins. But if you stare at this long enough, you'll realize that this is actually not the unique spin or flip error configuration that will give these constraint violation patterns. So here's another example. So this is the one I showed you just now. And here's another one that will actually give you the exact same constraint violations. And so you're led to ask yourself, well, which one is the more likely error? Right? And actually, there's many, many more. So it's not just these two. So for our work, we're going to consider several decoding strategies. So one is the simplest thing you could sort of think of, which is essentially the equivalent, or what I think is the equivalent of the majority vote for the minor embedding. So what you're going to do is you're just going to take a random spanning tree on your logical, you're going to take a random spanning tree on your physical graph, use that to map to a logical state, and then essentially do this many, many times, and then do a majority vote on those logical states. Another way, more sophisticated way, would be to actually find all the possible errors that correspond to the constraint violations that you found, and pick the one that actually requires the fewest number of spin flips. Okay? Now, actually, you can think of this as being sort of the poor man's version of essentially setting the Nishimori temperature to 0 artificially. Ideally, you would want to actually do this decoding at the Nishimori temperature. And of course, then there's the very nice weight 3 parity check method of Pastowski and Preskill, which I will point you to that paper for more details. Now, what's important is that essentially, these methods only really work very well for random errors. OK. So now there's the question of, and this is in some sense the big question, how do you compare the minor embedding scheme and the LHZ scheme? Okay? And how do you compare them fairly? Okay? Now, this, I think, will be very controversial, but this is what we did. Okay? We assumed we're going to use the exact same parameters for both methods using simulated quantum annealing. What does that mean? It means we're going to use the same temperature for both, we're going to use the same number of sweeps for both, the same type of spin updates, and the same annealing schedule. Okay? And the only optimization we're going to do is on the penalty strength. Right? So we're going to run both methods with large number of penalties and pick the penalty that maximizes the performance of each method individually. Okay? But this is not the unique way to do this comparison. Right? For example, as Wolfgang pointed out, there could be benefits of optimizing the annealing schedule for both of them separately. And of course, you can imagine that if you were going to build a quantum annealer based on the minor embedding method or a quantum annealer based on the LHZ method, you might actually have different sort of capabilities based on which architecture you use. And that's something, in principle, you should use in the comparison. But for us today, we're going to stick to this. So let me show you some results. So here is a single instance. Right? So this is an 8 logical spin problem. The JIJs are picked randomly from 0.1, 0.2, all the way to 1. And what I show in this plot is the probability of reaching the ground state for different penalty strengths. And there are different curves here. There are LHZ curves with no decoding, minor embedding curves with no decoding, and then LHZ curves with a majority vote. So this is with the random spanning trees. And then minor embedding with a majority vote on the chains. So let me point out a few important parts. So one is that at least for this instance, you see that majority vote, or the decoding, helps both methods only really for small penalties. And for high penalties, both methods essentially, or the no decoding and with decoding give similar results. But also you'll notice that there's actually the peak in the success probability is at some intermediate penalty strength. So actually having very large penalties is not optimal. And this is actually something we've all sort of learned, for example, on the D-Wave processors. Now, notice that, of course, here, the minor embedding method seems to outperform the LHZ method. But you might say, well, both of them are not doing great. The maximum here is not even 0.5. So what's going on? So for example, that was for 10,000 sweeps. Now you could do it at 100,000 sweeps. And what you see is that essentially both of them, their performance improves, but the minor embedding still seems to outperform the LHZ. Now you might say, OK, maybe this is just an artifact, or maybe this is just this particular instance that you cherry-picked. So what we did was we generated 100 instances, right, and ran all of them using, again, the same SQA parameters. And this is the plot you get when you plot the minor embedding success probability on this axis, the LHZ success probability on this axis. And essentially, anything to the right of this line means the minor embedding wins. And again, unfortunately, or fortunately, you see that the minor embedding is overwhelmingly favored by LHZ. So what I showed you in the previous plot was not a fluke. But now you might say, OK, look, there are much more sophisticated decoding strategies for LHZ, so maybe you should use those. Absolutely. So we now do things with minimum weight decoding, which turns out to be actually as good and usually better than the parity check method of Pastowski and Preskill. But of course, I want to emphasize that this minimum weight decoding is actually not efficient, whereas their method is. So now if you use that, and now what I'm going to do is I'm going to color code the dots according to the LHZ penalty strength, the optimum LHZ penalty strength. Now you see things are much more balanced, it looks like, right? And one thing you should notice is that it looks like LHZ does very, very well when its optimum penalty strength is very small. OK, let's go to larger system sizes. And now if I go to larger system sizes, it looks like things are no longer so balanced anymore. More and more of the instances are in favor of minor embedding, although for these SQA parameters, they're still doing, or both of them are not doing so great now. So you might wonder, though, well, what about all of these dots? There's something interesting happening there. And it actually turns out that this is actually an artifact of these small problem sizes. It turns out that this minimum weight decoding, when the penalty strength is 0, it essentially helps LHZ find the ground state very, very quickly, because essentially the errors are so dominant in the LHZ scheme, and the minor the MWD decoding essentially does its own optimization, and it turns out that the ground state of the optimization it is doing is the same ground state as the ground state of the logical problem, and that's why it works. So this is actually an artifact that actually very quickly disappears as the system size grows. So at least the conclusion at this point is that it seems that as the problem size grows, LHZ becomes less and less competitive. So now this question of the gap came up in the earlier talk. And it's, of course, very, very hard to determine this. But there's a very nice question that my colleague Itai Hen brought up, which I would like to sort of use, and it's the following. So consider in the LHZ case the 0 problem. So you essentially have the LHZ scheme, but you've set the logical problem to 0. So all you have now is n times n minus 1 over 2 spins coupled with 4-body terms. This is an instance of 4 XOR SAT. Okay? So you might ask yourself, well, what do we know about XOR SAT and quantum annealing? And so if you do the literature search, it turns out people know that 3 XOR SAT exhibits an exponential closing of the energy gap. And I point you to these 3 papers. So while this doesn't prove that the LHZ scheme will always have an exponentially small gap, the question I want to pose to you, the audience, is what is the loophole? Because I don't know it. So with that, let me just bring up the conclusions of my talk. So first, if you're going to make statements about the performance of various schemes on quantum annealing, it's important to have or use a relevant error model. So at least when you use SQA, it seems that the LHZ performance is not as favorable as minor embedding. And in our study, which at least I haven't shown you in detail, we at least attributed this difference in performance is really due to the fact that LHZ has a harder time to thermalize using SQA. And an open question, I would say, is that is this because of the worst gaps or a worse gap structure? But now, is this the end of the story? And I want to emphasize that no, it is not. Okay? LHZ has a lot of very, very nice properties, right? And we shouldn't forget those, right? So one, it lends itself to very nice decoding strategies, right? And you can imagine that if there's some innovative young person in the audience who can think of something better, then maybe you can imagine having a dramatic improvement in the success probability of LHZ. Of course, both LHZ and minor embedding can be further optimized, right? And I think, really, you have to optimize both completely to maybe be as fair as possible. Now, there are other advantages of the LHZ scheme which I've not highlighted in this work. And Wolfgang pointed this out, which is that in order to implement your logical problem in LHZ, you only need really precise control of the local fields. Okay? And in many implementations of quantum systems, we have much better control of local fields than we do of couplings. Now, why is this good? This is good because we know that as our Ising problems get bigger and bigger, this phenomena of J chaos becomes a bigger and bigger problem, and so precision is important. Right? So the fact that you can possibly control your local fields much better than you can control your couplings might be a very important thing. Okay? But there are also advantages to minor embedding, which I didn't highlight in this work. Right? So we all know that when you get your machine from D-Wave, there are holes in the graph. Okay? And you don't send it back just because there are holes in the graph, mainly because we know, for example, that if there's imperfections in the graph, we can snake our chains around those holes. Right? But what if I had imperfections in the LHZ scheme? right? If I punched holes in their graph, I mean, does the scheme still work? And I don't know, but I wonder if this rerouting idea from this Simon Benjamin et al. Paper is the answer. And then let me end with one final thought. And this is my personal opinion, and you can ignore it if you wish. My feeling is that, right, if we're going to implement all-to-all connectivity schemes, we can't just do it on the classical part alone. It has to be done in conjunction with the driver, right? And I think Itai and Federico, my colleagues at ISI, sort of started along this line, even though they were, I think, thinking about maybe different things in this work, and Itai continued it with Marcelo. And I think maybe we need to sort of really think about doing both together. And with that, thank you.
So let's start with a few questions here.
Hi, thanks first for the very interesting talk. In my experience, there's a point that you said last, that the decoding strategy can drastically improve like the success probability of the LHC scheme. That is something that I observed by just tweaking the minor belief propagation just a little bit. And it would just be an interesting question to you for your intuition. Would you say that the subpar like performance is due to the LHC or due to the decoding? What would you say in that regard?
If I had to guess, I would say it's, at least for the simulations we did, it's due to the LHC. And the reason is because what I see really when I do these simulations, and for example, you plot where the constraint violations happen. There are usually very few constraints that are violated. But what this means is that essentially a large number of spins have to be flipped to just get those tiny number. And I think this is the problem, is that essentially the errors look like a large order n number of spin flips. And then I don't think any decoding scheme, at least at that point, will help much. Yeah. Yes?
Hey, Tameem, great presentation, and I have a comment, but it's really less to do with the core body of your talk, but something you mentioned at the beginning about the thermalization. Can you flip back to that slide?
Sure. Let's see. What's the easiest way? So this is errors in the...
It was like the thermal aircraft.
Is it this one? Or is it the next one?
The one with the diagram.
This one?
Yeah, yeah. So you had sort of described that you have these potential thermal excitations, and they're very fast when the gap is the minimum, and then the likelihood of then getting thermally saved is very unlikely unless you wait a long, long time, which is actually like a very non-physical way of thinking about this, right? Because for every transition probability you have of going up, you have the same one going down, right? The only reason why it's faster is because your population in the excited state starts at 0, right?
Yes.
The moment you get a high population in the excited state, or even let's say a 50-50 split, then your rates are basically the same going up or down.
Okay. So you're right. Okay. So when it's 50-50, yes, right? But now so let's say what happened here is that you ended up pushing thermally a lot, but of course here when the minimum gap is small, you also get lots of diabatic errors, right? So let's just say for the sake of the argument, that now you actually even have more population up here than down here, okay? So you would think that at this point, as the gap is opening up again, you should get lots and lots of thermal relaxation, right? But the problem is that, of course, at this point, what typically happens is that your sigma x term, or your driver, is very small, right? The energy eigenstates are now getting very, very close to being computational basis states. And at least if you have like a dephasing bath model, essentially the relaxation rate becomes suppressed because essentially if you wedge, because it's proportional to essentially energy eigenstate 1, the bath operator, energy eigenstate 2, and if it's something like computational basis, sigma z, computational basis, this is going to be essentially very close to 0. So this is why, the relaxation here, at least if you use like the weak coupling master equation, will tell you that the relaxation here is very, very small because of other terms in the rates.
I agree with that, but the effect is continuous the whole way along.
Absolutely.
Okay. Any more questions? I think we have time for 3 more questions.
Yeah, actually, to follow up that question, so is there any way of changing your simulated quantum annealing algorithm to have sort of constant bit flip rates with some temperature model, or is that not possible within the context of quantum annealing? Like to have bit flip relaxation?
Well, I mean, so let's say, if you started in a very high energy state in quantum Monte Carlo and you ran it, right, it should thermally relax if the temperature is low enough. Yeah. So maybe I'm not understanding your question.
Well, it was talking about relaxation after the gap.
Yeah.
And the coupling to the outside world should be the same. So
yeah.
even if the X term is small, you should still have potentially significant bit flip relaxation.
So at least I think that intuition is not true in the weak coupling limit, right? So in quantum Monte Carlo, for example, we know that, so at least in the path integral approach, for example, spin updates become very inefficient when your Hamiltonian becomes essentially just the Ising one, okay? And in the past, people have said this is actually a good thing when you want to use quantum Monte Carlo to model things like D-wave, because we know there's this freezing region, right? So when the quantum Monte Carlo, the spin updates become less efficient, this is good because it's sort of capturing the freezing phenomena on D-wave processors, right? Now, in the master equation approach, the same freezing happens, okay, for the dephasing bath, because the rates are proportional to essentially the overlap of the one energy eigenstate, the second energy eigenstate, and the bath term, right? And if it's a dephasing bath, and your energy eigenstates are essentially or very close to being computational basis states, they're orthogonal, so that's why that overlap is very small, and both the thermal excitation and relaxation rates here are essentially 0. So in the weak coupling limit, even a master equation approach will tell you that essentially the thermal dynamics become sort of suppressed because of that.
So as we learned yesterday in the panel discussion, the quantum annealer may not be best for find the exact solution. So I don't know whether or not you have compared the performance of the two methods for an approximate solution.
OK. So we didn't look at whether either of them finds, or like just, what is the lowest energy state it found? We didn't do that. But what we did do is we actually compared how close each one of them was to the thermal state. Okay? And I can tell you, and you can ask, well, how did you find the thermal state for 120 or larger spins? What we did was we essentially ran parallel tempering on the classical problem for many, many sweeps. And we said, OK, hopefully it's thermalized, and that's good enough. And we compared the distance of LHZ, minor embedding, to the thermal state. And we found that minor embedding was actually closer to the thermal state. So yeah, but we didn't do, for example, a sort of a residual energy comparison. Although if I had, maybe I won't say anything.
So let's thank again Tameem for a very interesting talk.